This is part 3 in our series of lectures on proofs of theorems on finite sets. And in this lecture we're going to talk about the cardinality of the disjoint union of finitely many finite sets. So here's the statement of the theorem we're going to prove. If A and B are finite sets that are disjoint, then their union is also finite, and the cardinality of the union is the sum of their two cardinalities. As for all of the other theorems that we've proved concerning finite sets, this one seems completely intuitively obvious. But we'll find that this is actually a key result, and it will play an important part in the proofs of all of the remaining theorems we're going to do for finite sets. We're going to make use of the following lemma in order to prove the theorem. We give ourselves four sets, A through D. We assume that A and B are disjoint and C and D are disjoint. And we assume that we have bijections F1 from A into C and F2 from B into D. And so the lemma asserts that we can then define a new function, F, from A union B into C union D, given by this formula here. If X is in the union, then since A and B are disjoint, then X must be either in A or in B, but not in both. If X happens to be in A, then capital F maps X to F1 of X, and if X happens to be in B, then F of X maps X to F2 of X. Then this is a function, and furthermore, using the fact that F1 and F2 are bijections, we can prove that F is a bijection. I'm going to leave that as an exercise for you, but I don't think you'll have any difficulty proving it. Both the injectivity and surjectivity are going to make strong use of the fact that A intersect B is empty and C intersect D is empty. So make sure you're clear where you're using those facts when you write up the proof of the lemma. Okay, so now let's turn to the proof of the theorem. And on the top, I'm just reminding you what it is we're trying to prove. If A and B are finite and disjoint, then A union B is also finite, and its cardinality is the sum of the cardinalities of A and of B. Now it's possible, since A and B are finite, it's possible that A or B is empty. But if either A or B is empty, then the theorem is really obvious, because, for example, if A is empty, then A union B is the same as B, so the left-hand side is the cardinality of B, and if A is empty, cardinality of A is 0, right? So the result is really completely obvious in that case. So let's assume that A and B are, neither A nor B is empty, and that means that there exists natural numbers m and n, and there exists bijections f and g, such that f is a bijection from A into n sub m, and g is a bijection from B into n sub n. Now at this point we could use the lemma on the previous page to produce a function from A union B into n sub m union n sub n, but n sub m union n sub m and n sub n have a lot of overlap, and so it's not terribly useful to work with n sub m union n sub n. So what we do is we're going to modify n sub n in the following way. We let D be this union here, and that's maybe a better way of looking at it is this. What we do is we take all of the elements of n sub n and we add m to it. So then if we do that, then this set and n sub n have exactly the same cardinality, because we can define the following function h from n sub n into this set D by x maps to x plus m. Okay, it's an easy exercise for you to show that constant translation is a bijection, and so that shows that D and n sub n have the same cardinality. Now if you take the composition G composed with H, G maps B to n sub n, and H maps n sub n to D, so this composition is a bijection from B to D. Remember, we proved a long time ago that the composition of bijections is a bijection. So now we're in a position to apply the lemma from the previous page, because we have that A intersect B is assumed to be empty, and n sub m intersect D is also empty, because if you look at n sub m and D, here's D, n sub m runs from 1 up to m, and D starts from m plus 1 and goes higher than that, so they have no elements in common. And therefore, and furthermore, we have a bijection from A into n sub m, namely this F, and we also have a bijection from B into D, namely this G composed with H. So applying the lemma, we can define a function capital F in this way, and the lemma guarantees that that is a bijection. Now I claim that that pretty much gives us what we want. And why does it give us what we want? We're trying to produce a bijection from A union B into what? We're trying to show that A union B has the same cardinality as the cardinality of A plus the cardinality of B, in other words, m plus n. So we would like to get a bijection from A union B into n sub m plus n. Well, what is n sub m union D? N sub m gives you all the natural numbers from 1 to m, and D then picks up from 1 to m, and D picks up from m plus 1, 2 plus m, and goes all the way up to n plus m. So this union is actually n sub m plus n. And so we have our bijection from A union B to n sub m plus n, and that's exactly what we need to assert that the cardinality of A union B is m plus n. So you see here that in my proof I said the proof is completed by observing that n sub m union D is n sub m plus n. Well, here's a useful corollary of the theorem. Essentially, the corollary is generalizing from 2 sets to n sets. It says that if we give ourselves a natural number n, and we give ourselves n sets, each of which is finite, and we assume that the sets are pairwise disjoint, then the union is finite, and the cardinality of the union is the sum of the cardinalities of the individual sets in the union. So the theorem that we've just finished proving is the version of this theorem with n equal to 2. So it's sort of a rule of thumb that if you can do something for two sets, then you can do it for any finite number of sets. And the device for making that work is induction. So the proof is by induction on n, and I'll leave that as an exercise for you, but just to say a couple of things about it, you would let capital S be the set of all n, such that one can do all of this. And so the result that 1 is an element of S is completely obvious, because if you just have one set, then both sides of this equality are identical. And then you say, well, suppose that n is an element of S, and then you want to prove that n plus 1 is an element of S. So you have to give yourself n plus 1 finite sets, and the union of n plus 1, of those n plus 1 sets can be viewed as the union of 2 sets, namely the union of the first n of them together with the very last one, a sub n plus 1. And then you would apply the theorem that we just proved and the inductive hypothesis to deduce that that union is also a finite set, and that we have the required formula. So I'll leave that for you to sort out the details. Now it turns out that the next few lectures, so I'm going to do, I guess, 4 more lectures for you on sets, on finite sets, and every single one of them will basically be proved fairly easily using this result. So let me list what are the kinds of things that we're going to do. And I emphasize that I understand all of these results are intuitively completely obvious, but nevertheless they require proof. Any subset of a finite set is finite. If A is a finite set and C is a subset of it, then A minus C, the set theoretic difference, A minus C, is also a finite set, and its cardinality is the cardinality of A minus the cardinality of C. If A and B are finite, then the union is finite, and the cardinality of the union is the sum of the two cardinalities minus the cardinality of the intersection. So this is a generalization of the n equals 2 version of this corollary, but it doesn't make the assumption that the sets are disjoint. So this is a more general result, and it's what's known as the principle of inclusion-exclusion. And finally, we're going to prove that if A and B are two finite sets, then the Cartesian product of them is also finite, and the cardinality of the Cartesian product is the product of their two cardinalities. 1 and 2 are going to make use of the n equals 2 version of this result, and 3 and 4 are going to make use of the more general result of the corollary. So why don't you think about how one might use the theorem and the corollary in order to prove 1 through 4. Think about it, and you'll see how I actually do it in the next 4 lectures.